Hello again, welcome back to CET3116. In our last lecture, we reviewed synchronous counters. And so far, all the counters that we have discussed are counters that count up. So they increment the counting. Of course, we're also interested in the possibility that we can also count backwards. And that's what we know, and that's what we use with down counters. Okay, so many applications for that. In this case, we're having a sequence that pretty much goes backwards. The only thing here, and the trick with the up counters in both cases, the synchronous and asynchronous, the carry is taken from the Q naught. So in the case of ripple counters, the one that we have reviewed that counts up, we take the output non-complemented of the flip-flop, and then we feed the clock to the next flip-flop on the right. In this case, we're not doing that. We're taking Q naught. Okay, and then we want to start looking just again ripple counters, but in this case down counters. Usually we use a preset to start counting in the maximum count, not necessarily always true, but these examples that we're going to be discussing use this form. Okay, our first example is going to be a down counter of 3 bits ripple. So see that all of 3 flip-flops have, as before in a ripple counter, the J and K flip-flops are such that both inputs J and K are tied to 1. In other words, we're using a toggle mode. If we look into the truth table, which is given here, that would be the count from 7, 6, 5, 4, so on and so forth, until we reach the 7 count. In this case will be 0, 0, 0. And then if we keep counting, then we sort of go backwards to 1, 1, 1, which is 7, and then back to 6, and so on and so forth. So wrapping around. See that the clock, as I said, is fed with the inverted output, or the complemented output, the Q naught. However, our reading is provided by the non-complemented output. So we're reading directly the non-complemented output. All right? So essentially, it works pretty much as the regular up counter, ripple counter. We started doing a preset before completing the first time, the first clock. Again, remember, we're using JK flip-flop falling edge. So that's why I depicted the falling edge with an arrow. Okay, see what happens. Exactly as what we have in the first case of a ripple counter, the flip-flop 1 is a toggle flip-flop that only receives the clock signal, and initially we're in 1 because of the preset. Okay, so we're going to start at this point. If we have a preset, we are now in 1. When the clock comes, then we force a toggle. Because we have a toggle, we need to go back to 0, and then 1, then 0, and so on and so forth. For every one, this is the rightmost column of the truth table. Toggles every row, 0, 1, 0, 1, 0, 1. No difference at all. Now let's take a look to the complemented output, that the one that's going to be the clock for the next flip-flop, which is the FF1 Q0. Of course, is completely reversed, is the inverse of this signal. And this is going to be the clock. This is going to be the clock for FF2. So see, all these are flip-flops that are first starting with a preset, start with 1, and every time the clock comes and goes down, for instance, in this case, because it's a falling edge type of clock, here, 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 and here, there will be a toggle, there will be a change. So let's see the flip-flop 2. This is the flip-flop 2, right? Evidently, we start with 1 because of the preset. At this point, we need to toggle. So we go from 1 to 0. The next falling edge of the clock is here. We need to toggle. So we're in 0. We go back to 1. Next falling edge of the clock is here. We're in 1. Go to 0. And here, we're in 0. Go to 1. Now, this is FF2. The complement will be the clock for FF3. All right? And this is FF3, initially 1 because of the preset. However, the first change occurs with this. The clock goes from 1 to 0. And then we toggle from 1, and we preserve that from the preset, okay, until this first time to change. The next will occur right here, and this is a toggle, in this case, from 0 to 1, because we did that from 1 to 0, right? So it's pretty simple, very straightforward. The only thing that you need to keep in mind is that we're using the complemented output to feed the clock of the next flip-flop. Okay, and this is the complemented output. We are not using any other stage. That would be the clock if we had a next flip-flop or extra flip-flop for counting 4 bits. All right, this is supposedly to be before questions. Ideally, you should take your time and think what would be the output signal for both flip-flops, and just they follow exactly what we did at the beginning. The only thing is that we start, instead of 1, we're doing 0. We're doing a clear. So Q will start with 0 for both, and Q0 will then be 1. So that pretty much doesn't change much. So FF1 is this. Remember, the inverse of FF1 will be the opposite. And this is the clock that we feed the FF, in this case, FF3. Well, I need to fix that. Okay, this is FF1, this is FF2. Okay. And the case here is, let me fix that right away. 2, and this is FF1. Sorry about that. Okay. And this is the this is the clock for the FF2. This is FF2. It will be changing when the clock goes from high to low. Here, high to low, then there's a toggle here, another high to low here, and it's another toggle, and so on and so forth. Exactly as we did before. All right, good. You figured out that before? Perfect. Here's another modification of this down counter, and we're using also 3 bits ripple down counter, but the main characteristic here is that stops once we reach the 0, 0, 0 count. Okay, we reach the 0, then we stop. What exactly is the difference? Well, if you look, well, the first flip-flop is not tied to 1. So it's not always toggling, right? However, the case is that we also have the output. So we take a sample of each one of the outputs, and then we simply OR these three outputs together, and that's what we feed here into the first flip-flop, which both have, of course, J and K tied together. See, what's going to happen is we expect that when we reach 0, 0, 0, we will have here a 0. And when we have a 0, then we reach a hold for this flip-flop, and they stop everything. Okay? So we start with 1, 1, 1, right? And any of these points in the sequence, you're going to notice that any of the outputs is 1. If that's so, if any of these outputs as is required in the truth table is 1, that means that the J and K both will be 1, and this will be toggling. So it will be toggling with the exception when the three inputs A, B, and C reach 0. So in this case, we stop everything and stays 0, 0, 0. All right? So here's the graphic for the flip-flop. And essentially, it's a 3-bit down counter in which we initially do a preset. With the preset, in this case, we force a 1. This is the clock, as usual. Remember, because it's a preset, that will force that each one of these flip-flop will have initially a 1 in the count, so that makes 1, 1, 1. And then we start rolling back, counting down. Okay, in this fashion. That's what we know, exactly as we did before. Okay, in all these counts, remember, but this count number 7, J, K in this flip-flop will be 1. Okay, well, we start that, we keep doing, see, and at the last point here, we notice that FF1, that will be A, this is B, and this is C, we reach the 0, 0, 0, and then we stop right there. Okay, 0, 0, 0. Okay, that's pretty straightforward. Remember, still, I mentioned that ripple counters are not that good in practice. However, I'm showing you one way to implement down counter using the ripple counter. I want to give you an example. Of course, we're going to come back and revisit the down counters implemented in synchronous mode. Okay, so synchronous counters that counts down. The idea is essentially the same thing. But if you see that when we do an up counter synchronously, and you look into what is going on with the outputs in each one of the flip-flop, and you see, well, what is the correspondence with the reverse, with the complement sequence that each one of those take, everything will make sense. Okay, so in this case, this is a counter, right? I want you to pay attention to this because probably we want to be using this model for the project or the second lab. And you will basically build a variation of this one. So this is 3 bits. You will need to build a 4-bit type of counter, up-down counter. This is a synchronous counter. We're using still the JK flip-flops, and we have an array. If you remember how we use the AND gates the AND gates in the synchronous counter of 3 bits. Remember, if you look into the truth table, whenever you want to force the change in the most significant of the bits, you have A and B both in 1 will provide a transition to 1, 0, 0, right? So in this case, we use an AND gate, and then we bring the inputs from A and B, and when both are 1, then the AND gate will be 1, and that will go feeding back into the first flip-flop, and they will make a toggle, right? Well, not to the first flip-flop, to the third flip-flop, okay? We'll make a toggle. All right. In this case, we're doing exactly the same thing. However, you may notice that if we look into the pink part, this pink part is just an up counter. So we can choose with the up down here whether we want to be using this segment of the branch or this one down here. Okay? What we're using at this point, that doesn't have anything to do with the array and the forcing of the toggling that we discussed before. But this is something different. The fact that we have this choice, red or pink or blue, that means that we're using either to count up, like here, or down. When we choose down, see the inputs here, what I'm saying is the first input that I'm applying to the next flip-flop. This is kind of reverse. This is the least significant. This is the one that we toggle. Remember, this is the next significant. It's the most significant. It's kind of a, we're sort of swapped. And this should be on the left. This should be in the middle, of course, and this should be in the most right. Okay, least significant, and this is the most significant. Okay, but this is the diagram that I found in one of the books. So the idea is that we're bringing, for counting down, the outputs from the complemented. Okay, so in this case, we're using A0 to feed the next stage. When we did that in the positive, we bring directly from A to J, K. Okay, they were tying, and then now we're doing this from A0. Okay, and here we're doing exactly the same thing as before. This is the second stage to the third stage, and we use this AB. Of course, we need an extra pin in this end, similar to what we did here, because this allows us to be sure that this is the segment that we are using. In other words, for selection. And then you see, if we have a 1 here, one up, this one will be 1, this one will be on 1, and that will be like I'm selecting this branch. Okay. In the meantime, if this is 1, this will be 0, and this is not, this is 0, and this is 0. So if we, in other case, we select to go down, that's 0 here, this 0 here becomes a 1 here. So this is a 1, this is a 0, nothing comes through here, and everything goes through the blue part, okay, which is the branch that we will be using for counting down. Okay, very clever design, very interesting. The case is that we can extend that. If you look into the truth table, we can extend that. I'm going to show you later that. If you review the behavior of this counter, what we have is simply the following. Well, we select the up and down with this selection. First cycle, we're doing exactly that. Our cycle goes, our clock goes like just like that. We make the choice to count from up to down right in the middle, right here, before the clock changes from up to down. And this is the sequence of the outputs that I have in the first case, identically as we did before. Now, we're counting up here, right? See that that's exactly the same thing. At this point, because 1 in this case is here is toggling, then we toggle here. It's up, we toggle here, and in the same case, this is a whole, right? At this point, it's a whole because it's a 0, and then we remain here. That's the same behavior. The only thing that's different, it starts right at this point, okay? And then what we're looking here actually is, in this case, is the complement. We're looking at the complement of each one of those. So we start going from 0, 0, 0, this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, right? We still go to 1, 0, 0. And 1, 0, 1. So we were able to count up to 5. Now, what happens here is now we start reverting everything, and then we're looking like back, because we are using to feed the next stage of the flip-flop are the reverse. It's kind of looking into the complement of the outputs, and this is what we're going to have. Okay, there will be at this point 1, 0, 0, right? All right, and then that would be 1, 0, 0. That's 4, 3, 2, 1, and back to 0. Okay. Well, I'm gonna leave you with this. We need to give some more examples of the synchronous down counting. But I guess if you understand this really well, you will not have any problems deciding or working with the project. Well, thank you so much.